Hello friends, welcome to Study Algorithms, a place where I simplify some basic programming concepts for you with some really to easy understand examples. If you are new to this channel, I want to let you know that you can find a text-based explanation to all the content on this channel on the website studyalgorithms.com, a pretty handy website to help you out with your problem solving skills. Over some of my previous videos, I have talked about how can you compare two algorithms or what is actually the time complexity of an algorithm. And I even discussed the big O notation with you. But the question is, how do you link all of them together? Do they all serve a single purpose somehow? In this video today, we would be looking at exactly that. We would be understanding the rate of growth of an algorithm based on the analysis that we have been doing up till now. So, if you want to just brush up your skills, I would recommend you to go over some of the previous videos, of which I have provided the link in the description below. Without further ado, let's get started. First, I will tell you what do you mean by the rate of growth of an algorithm and why is it so important in computer programming. Going forward, we will visualize these rates of growth on a graph so that this concept sticks in your mind forever. So, what do you mean by the rate of growth of an algorithm? If you think about it, an algorithm cannot grow by itself. It sounds very weird and it would be actually funny, right? But still, you might have heard this term a lot. An algorithm cannot grow, but certainly the time taken by it to solve a problem can grow. So basically, an algorithm is a series of steps which you perform to solve your problem, right? And this problem can have a sample input size. Think of it like a recipe. Suppose you have to make a meal for one. You have a recipe, you follow it step by step, and ultimately you would have a delicious meal ready. But think about now you're making the same recipe, but this time you're making it for 100 people. Your total time would increase, right? You would have to chop more vegetables, your preparation time would increase, you would have more utensils to use, and so on. So, if you compare this to computer programming, your recipe relates to the algorithm and your meal size is your input size. So, if your input size increases, the time taken by an algorithm to perform the same job would also increase. For example, if you're writing a program to sort some numbers, it would definitely take more time to sort a million numbers rather than sorting just 10 numbers. This is why we need to understand the rate of growth of an algorithm. You need a way to determine that, okay, if I add 10 more numbers, how much time will I take? If I add 1,000 more numbers, how much more time you will need? If this concept is now clear in your mind, let us try to link the rate of growth of an algorithm with the big O notation. We would be doing this by taking some examples so that this concept becomes clear in your mind. So let's get to it. To start off this example, let me explain you the entire setup first. Over here, I have all the different kind of big O notations we would be representing on the graph. On the x-axis, we have the input size. So if you move along the x-axis, you are increasing the input size. And on the y-axis, you have the number of operations an algorithm is taking. So on the lower half, an algorithm is taking less number of steps, and moving forward, your algorithm is taking more number of steps. To simplify our analysis, we are assuming that one step takes 1 nanosecond. That means if your algorithm is taking 10 steps, the total time is 10 nanoseconds. And if your algorithm is taking a million steps, then your algorithm is taking a million nanoseconds. So in a way, you can say that the y-axis simply determines the time taken by an algorithm to complete. The last thing we have is our table. In this table, we would be populating the number of steps taken by each of the big O notation. And then using this table, we would plot our values on the graph. So we would be determining how much time does it take for 5 input size, how much time does it take for 10 input size, then 15, to all the way up till 1000. If this setup is clear in your mind, let us begin with order of 1. So order of 1 simply means that no matter what is your input size, you are taking a constant amount of steps to complete it. Let us say that the algorithm you chose is completing the task in 42 steps. That means if your input size is 5, you still take 42 steps to complete. If your input size is 10, you take 42. For 15, you take 42, and then so on. So when you plot this value on the graph, it would look something like. So this graph is showing that no matter how much is your input size, you still take a constant time, and that would be 42 nanoseconds. Moving on, let us look at order of n. Now, order of n means that the time taken by an algorithm to complete depends directly upon the input size. So, if your input size is 5, you are taking 5 steps. If your input size is 10, you are taking 10 steps, and then so on. So let us try to populate this table. For an input size of 5, you take 5 steps. For an input size of 10, you take 10 steps. And then 15, then 20, then 25, and then so on. If we plot these values on the graph, it looks like a straight line that is inclined at a 45-degree angle. So this would look something on the graph like. So you can see that when the input size was small, the order of n algorithm took less amount of time. But as soon as the input size increased after a certain limit, then the order of n algorithm actually took more time to complete. Similarly, now let us move forward towards order of n squared. An order of n squared means that the algorithm you are choosing takes squared number of steps based upon your input size. So if your input size is 2, you are taking 2 squared, that is 4 steps. If your input size is 5, you are taking 5 squared, that is 25 steps. Based upon this, let us try to populate the table now. So when your input size is 5, you take a total of 25 steps. For 10, you take 100 steps. For 15, you take 225 and so on. This looks like a quadratic graph. And when we plot this on a graph, it would look something like. As you can see from the table and from the graph, as your input size increases, an algorithm which runs in order of n squared time takes a lot of steps to complete and hence a lot of time to complete. For a certain input size, you can see that order of n squared completes at a higher time, order of n completes at a lower time, whereas order of 1 completes in an even lesser time. Now, let us move towards order of n cubed. Just like order of n squared, an order of n cubed algorithm means that for n input size, you take n cubed number of steps. So if your input size is 3, you are taking 3 into 3 into 3, that is 27 steps. So based upon that, let us try to fill this table real quick. So 5 steps would mean 5 cubed, that is 125 steps. 10 would mean 1000 steps. 15 would mean 3375 and so on. When you try to plot this on the graph, this would look something like. As you might have guessed, you can see that from the graph and from our table, this algorithm of order of n cube takes a drastic amount of time even for a small input set. Hence, certainly this is not a good choice of your algorithm. Let us now try to look at order of log n. Now, when we talk about log n, it means that for an input size of n, we are taking log n amount of steps. And in this case, the log base is default to 2. So the value of log 4 is equal to 2. The value of log 8 equals to 3. The value of log 16 equals to 4. The value of log 32 equals to 5 and so on. To speed up our process, I have already calculated these values using a calculator and even you can verify them. So when I do log 5, it would come something like log 10 would be, and similarly, I would fill in the remaining values. Now, when you plot these values on the graph, this would look something like. As you can see from the graph and from our table, As the value of n increases, the value of log n does not increase that much. And an algorithm which runs in order of log n time is actually better than an algorithm that runs in order of n time. The basic idea behind this entire example is if you want to determine any other time complexity and you want to see which algorithm would perform better, you can plot out values like this and see for yourself which algorithm is actually performing better. Suppose you want to determine the time taken by a certain algorithm at this point of time. So you just point it out and draw a vertical line from over here. Then you can know that order of n is taking this time, order of log n is taking this time, order of n is taking this time, order of n square is a higher time, and order of n cube would be an even higher time. You might have seen this graph in a lot of places before, and I hope this starts to make a little bit more sense now. I hope now you get a better idea about why the big O notation can help you to determine the rate of growth of an algorithm. This also helps you to select a specific algorithm while you're solving problems. If you know that you have to solve a very small problem, it actually doesn't matter too much whether you select an algorithm that performs in order of n square time complexity or an order of log n time complexity. But as your input size starts to increase and you get really sensitive about the time taken, then you need to be really clever about which algorithm you are selecting. As per my departing thoughts, I want to know what is the most common time complexities that you encounter in your day-to-day programming problems. Let me know your thoughts in the comment section below, and I would really like to chat about it. If you found this video helpful, please do consider subscribing to my channel and share this video with your friends. This motivates me to make more and more such videos where I can simplify these programming concepts for you. Until then, see ya.